Okay. Now we're all here, more or less. All right. Okay, digital video. We'll talk a bit about sampling and bit depth and sort of explain some of the numbers behind the encoding and compression and processes, etc. Oh. So the hardware, the method, if you will, the basic building block of any kind of digital sample situation is the A to D converter, also called the D to A converter, but not always the same. So understand that an A to D converter and a D to A converter are two different devices. This box, for example, has both, but they are distinct devices. Sometimes you only need one, and just to explain, it's analog to digital and then digital to analog. So of course, the world as we live it is an analog world. Everything we see and do and interact with is not digital, it's analog, and unless of course you subscribe to the conspiracy theories that this is all a hologram. And then on the other side of the coin, once you've finished manipulating the material, recording it, compressing it, editing it, and then you want to feed it back to via YouTube or television or whatever you want to do to the audience, they witness it in analog. The screens, the headphones, all those things convert the digital numbers back into analog. So that's the D to A side of it. So there's always an A to D and a D to A in the digital world. All right. And that's just, this piece of hardware. I mean, these devices, some of them are chips. All of our computers and phones and things have these entire devices on a chip or a fraction of a chip. Some of them are quite large boxes. And on the other side of the coin, you can get studio quality D to A converters that are 3 or 4 inches tall and 18, 19 inches across. Usually they have multiple channels. So there's a whole gamut of D to A conversion that goes on throughout our world. The reason it's worth mentioning is that this is one of the pieces of hardware that sucks up a lot of energy. It takes a lot of electricity and battery power to make these things work, no matter how small they are, because there's a lot of math going on right off the bat. Like you haven't even compressed thing 1 yet, and you're digitizing it, and that's taking a lot of processing. So it's just, just as give you a guidepost as to what's going on. So what does an A to D converter do? What the A to D converter does is it changes what's called a continuous analog quantity, which, as we know or should remember, is the world. The world is a continuous series of events. There is no hesitation. Time moves in a fluid fashion. And as a result, events and reality, things that are moving, things that are listening, talking, speaking, are all happening continuously. So the A to D converter takes that continuous experience and then cuts it up into discrete numbers. And basically those binary numbers, that on and off pulse, right? This is a video I was going to show you, but I probably aren't. Well, should I? It's really cheesy. Oh, yeah, you know what? I will link to it in the, I'm going to just have a quick peek.
44,001.
Yeah, no, he says what I'm going to say. So I'm just going to, I put it there for illustration, but I think today we need to get moving and I don't want to sort of slow down the flow. So when we talk about sampling an analog signal, if we look at this graph, and I don't know if you can see it and squint, don't worry about the numbers themselves. Just understand that there's an X, Y axis of the graph, right? So along the bottom, we have the intervals of time, and along the side going up and down, we have the quantity. And we'll get to that again in a minute. But if you look at this graph, the analog pulse at the very top, that smooth curvy line is in fact smooth and curvy because the world is constantly changing, so that any distance between points, well, first off, in analog, there aren't really points at all. It's a continuous experience, but in order for us to even graph it on a piece of paper, we have to mark off points. And the transitions between all those points are very smooth and fluid. When you go to digital, you capture those points and you end up with a string of numbers that you have in the middle there, which kind of is represented by, so those little, for those that know and those that don't, those little sort of tooth-shaped figures on the graph right above that middle string of numbers is in fact the actual graphing of binary numbers. They are basically straight up and down, on and off. So they go straight up when it goes on, it stays up until the next off pulse and then goes down. So this in fact does represent what binary numbers look like on a graph. And then below that, you'll see the string of ones and zeros, which is the binary numbers. And then below that is the analog digits, the decimal digits. And I apologize if it's really tiny, but that's what's going on. You can see it in the PowerPoint, in the PDF you have on on Learning Hub, and you can zoom in if you want. So the top, again, just a reminder, the top is the analog experience, that kind of continuous fluid world that we live in. The second one is the numbers that come out of that experience. And then the third one is the playback. So we now take the numbers we've created on the top by looking at that analog experience, and every single one of those dots on that top curve has been assigned a number, which is now that second row. If we go down to the bottom graph, we take those numbers and then try to replot them on the graph. And you'll notice right away that they're not fluid. And they aren't and never will be. This is an exaggeration, but is in fact exactly what a digital playback looks like on a graph. So in other words, if the top graph is the analog reality, the bottom graph is the digital approximation. Now, the only thing you can really do in the world of digital is make those sharp corners and sort of flat sides smoother, but you can never eliminate them completely, right? And we'll get into more detail about that in a minute. But understand that digital is always going to be an approximation. So the first thing, for example, is that between each event on the graph at the top, those dots, in the digital world is a continuous steady state. In other words, if that first dot is 4, it stays 4 until the next dot, which is 6. In the analog world, between the 4 and the 6 dot, that very first part of the curve, the line's already changing direction. Right? It's increasing from 4 up towards 6 in a continuous motion. That doesn't happen in digital. It jumps from 4 to 6, right? And then up to 7, and then down to 6, and then down to 4. And then, as you can see, the graph is quite jagged. So understand that this is the real, how am I going to explain this without being too confusing? This is the real world reality of digital. So when people say to you that digital is not perfect, that digital signals don't accurately capture the analog world, no matter how high the sampling rate, they are technically right. The problem is with that argument, and this is where you get into the punch outs at discussions about this, is that if the spaces between the changes in digital at that bottom graph are close enough together, then the human mind cannot distinguish between abrupt changes and smooth transitions if those abrupt changes happen fast enough. It's a bit like the frame rate in video. If the changes between frames happen fast enough, our brain doesn't have the ability to detect the transition and just sees it as one continuous event. So my point being, audiophiles will argue up and down a blue streak that there is no way you can ever reproduce analog sound in a digital fashion. Technically, that is correct. Technically, these transitions, no matter how smooth they are in the bottom graph, will always be there. In reality, do we care? Do we notice it? Right? Is it, to paraphrase, worst sound ever? No. Right? And that's, as I say, that is I mentioned that because that is the talking point, the argument point that almost everybody gets into when they talk about digital versus analog. And just as a sidebar, as an audio guy myself, who was an audio guy anyway years ago, people who talk about things like analog is more lifelike and warmer, things like that. So some of that lifelike and warmth is distortions and signal degradation that's built into the analog process. Analog suffers from a lot of different issues, in regards to circuitry, and there's a whole bunch of technical reasons for it. But a lot of what people call warmth, for example, in analog, is actually distortion. But God forbid you tell them that, because then you'll have a complete fight on your hands. So yes, analog is. The perfect analog solution would be a system that records reality without any other extraneous data and noise, anything else, and that's never going to happen. Digital is as close as we can get. All right. So let's just get a bit more detail about that graph. So now we've moved on from this kind of really crude approximation to this sort of idea where we now have sort of labels and tags on things. All right. So here we have 3 different graphs moving from left to right. You have more steps you're measuring. So you can see that it's the same curve. So if you look at the blue curve in this graph, that is the analog data that we're trying to digitize, right? If you look at on the left-hand side, this should be the other way around, but let's start at the most refined. The left-hand side has what's called 4-bit quantization, which means that there's 4 bits of data per per step. And the red stair step, which is the digital reproduction, right? So the blue curve is the analog reality, and the red stair step is the digital reproduction. That red stair step is much, much smoother on the 4-bit than it is on the 3-bit or the 2-bit. And that's because the 4-bit has more data, 4 bits, right? More data than 3 bits or 2 bits. And we're talking digital bits here now, right? So 2-bit quantization has 2 bits, right? So there's only 2 places you can store the data. Those bits can either be ones or zeros. The 3-bit quantization has 3 bits where you can store the data, and the 4-bit has 4 bits, right? So why is this important? Why does this matter at all? Is because when you take an analog curve like this really crudely drawn red squiggly line, and you take a measurement, which is what we're doing when we digitize. Remember that. The whole point of digitizing is to measure what's happening and then reproduce it later. If we take measurements kind of any old place on this curve, you'll get this kind of shape as a result. Because remember, when you take a digital measurement, if you go back here again, when you take a digital measurement, what you do in your finish is you connect all the dots you've created. So we go back here again, right, just to be sure. We take the measurement from the top, we get the numbers in the middle, and then we redraw that measurement on the bottom by connecting all the points together. And this is the shape you get, right? So if you don't measure correctly, it's entirely possible to get a really skewed result. And this is an honest, kind of reaction that happened early in the days of digital, when they just took measurements any old where, and then you got this blue dotted line, which has no, or this purple dotted line, which has no resemblance to the original analog squiggly line, right? So if you understand what's happened here, is the analog squiggly line was measured at 1, 2, 3, 4, 5, 6 different points. Those lines, you see the black lines coming up from the bottom. And then we connected those points together when we took the digital, went back to analog, and we got this shape instead, right? So what's important about sampling in digital is how often, which is the sampling rate. And that, in other words, that's the number of times we make a measurement. So these lines that go up to this curve are the times across the bottom, right? So we go back here, just to remind you, on this graph, it's time across the bottom. So sampling rate is how many times do we measure, all right, in a given time frame. Usually measured in times per second. We often use the word hertz because hertz is frequency, which is also another word for times per second. So you'll hear numbers like 44,100 or 44.1K hertz sampling rate for things like CDs, or 48K hertz for audio. And that means that you're measuring the analog audio signal 48,000 times per second, which sounds pretty good, right? And it is kind of, but it still has its flaws. And then the next, that rate, by the way, has its flaws. The next step would be how much data did you measure at that instant? Okay, so 2 things are going on. We're looking at how often do we take a measurement, sampling rate, and then how much data are we measuring with? So don't confuse this. The amount of data is the same in the quantization, no matter how many bits you use. What's different is how many steps do you have? Let's go back here again. How many steps do you have in that measurement? Okay, and that's the quantization. So the curve in all 3 of these graphs, that blue curve is the same height, right? But in the first example, well, let's reverse it. The curve is the same height. In the right-hand example, the far right, we have only 3 steps, 0, 1, 2, 3, right? On the middle one, we have 7 steps. And on the left-hand one, we have 15 steps. Same curve. But now what we can do is we have much better refinement between points in the curve. So the played back curve, if you want, that stair-step shape, will be closer to an actual curve. It'll never be, so understand this as well. When you play back digital, you'll never get that curve back. You'll just get a very, 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 very smooth stair-steppy graph. So that left-hand one, the small stair steps, those stair steps get even smaller, but they never go away. That's something called aliasing, and we'll talk about that a little bit later. All right. So I'm going to stop here just for a second. Any questions? In fact, I might just pause the recording for an instant to stop the share, pause the recording. Thank you. Okay. So, let's go back. So Just to go through the cycle, we have the analog signal. Two things are happening. We have sampling on the left here and quantization on the right. Now they're both happening at the same time. This has just been divided to show you the different characteristics. So on the left, we have the sampling, and you see the blue lines coming up from the bottom. Those are the intervals. So the space between those lines is how many times per second that we measure the graph. The dots at the top of the line is where that sample happens in the graph. So as the analog signal is moving through this graph shape, the digital samples are happening at those points in time. And then the quantized signal is the number of steps. If you look on the right-hand side, the quantized signal is the number of steps that we have to measure the data. And then the digital signal is a combination of both, right? All digital signal is always some sampling and some quantization. So if you think of to use a metaphor, if you're thinking of counting sheep, let's say, as they enter a pen in a farm, you open the gate and you have 50 sheep, let's just say. You open the gate and then you wait until all the sheep are in, and then you close the gate and you count them all. That's one sample with 50 steps, right? You've made one measurement. Now, if you count the sheep every few minutes, every few seconds, so that you mark down the time, at 5 minutes, there were 2 sheep in there. At 10 minutes, there were 4 sheep in there, et cetera, et cetera. Now your sample rate is much lower. Your quantized numbers are lower, but then your overall result, you're still going to end up with 50 at the end of it all, but you're going to have a different graph, right? So this is all happening at the same time with digital. So more samples better? Yeah, ideally. So if we look at this graph, now you can kind of see the result. As we increase, if we look at the middle bar, you see as we increase the number of steps in time that we sample, they get closer together as we go across, just to see what the wave lane looks like. The top wave is the analog wave. It's always the same shape because analog is always analog. But the bottom output, as you progress through more and more samples per second, you can see that on the right-hand side of that output, it's now starting to look more like the top. Now the top, by the way, the reason the top looks kind of jaggy is because when you blow up some of these graphics, and I did a terrible job on this graphic, the lines get jaggy. That line should be smooth. Just imagine that top input line is smooth. But the bottom line jaggies are definitely there. They're much more pronounced and they always will be, but you can see they're closer together. So it does start to resemble that top curve. So you can see the higher you sample, the better it's going to be. Now, this is a challenge because we're back to price, speed, quality pretty soon, because that sampling takes a lot of energy. It can take a lot of quality to get the proper numbers of sample rates, et cetera. So at some point, there's a trade-off. You have to say, I have to stop sampling now. I have to cut my sample rate off at a certain point. Because the other thing is too, the higher the sample rate, the more data you get. Because every time you take a sample, you're storing data, right? Every sample has a quanta that goes with it, right? And that quanta is that amount of data. It has to be stored. So the more times you sample, the more data you have. Right? So that's all this classic price, speed, quality trade-off. Is there an ideal sample rate? No. You'd think, again, more better, and the faster you can, the better. Yes, that's true to a point, as I've already explained. If you oversample, in other words, if you start to capture more data than you need, for example, if you're capturing so much data we don't need it, then you're just going to digitize stuff we're never going to see. It's going to be made irrelevant in the compression scheme, which comes later, by the way. It'll be made irrelevant because we don't notice it, and you've wasted time and energy sampling it, right? So there's a whole bunch of reasons for the fact that there's no such thing as an ideal sample rate. Different rates for different tasks, right? That's the trick. I mean, one of the things, for example, CDs, if you go back in the old days, when CDs were first discovered and invented and unearthed by archaeologists from the tombs of ancient Egypt. Anyway, however they discovered CDs, and I'm joking, I know how CDs came to be. Anyway, CDs, they settled because of the size of the disk and how much data it would hold. They settled on a sampling rate of 44.1 kilohertz, 44.1 or 44,100 samples per second. And there will be people, and I'm kind of one of them, that sometimes you can tell music from a CD from analog music because the sample rate of CDs is not quite high enough to capture some of the harmonics. So then when they came along with digital equipment, probably about 10 years or so after the CD came out, somewhere in the mid-90s, they settled on 48. they gave it a bit extra headroom. So most audio equipment nowadays, cameras and stuff you guys are dealing with, is going to have a 48 kilohertz sampling rate. Some of them will still have the old-fashioned 44.1, but that was because of CDs. But the compromise on 44.1, 48 is a better sampling rate, but the disc wouldn't hold that much data, right? So no ideal rate. There is a minimum now, and that is one thing. The minimum rate you should get is something called the Nyquist rate. And the Nyquist rate is at least double the highest frequency you want to capture, right? And why is that? Because here's the Nyquist rate illustrated. If you double the rate, in other words, if you imagine that one complete analog sweep is the curve going up and down, right? So if we look at these black lines that are going up and down on this graph, two of those black lines is one analog cycle, right? From zero to peak to zero to trough to zero again. If I can, let me get the mouse out here. So this here is one analog cycle, right? As always has been, always will be. And that's because if you join these 2 points together, you have that circle, right? You've got a complete 360-degree travel going on here, right? So that's one analog cycle. Well, if you want to get this shape, you need at least two samples. At least two, right? Now, more would be better, of course, but at least two. And two is what's called the Nyquist rate. That's double the sampling rate of the original source. So if the original source here is, let's just say for the sake of argument, this analog is 1 cycle per second, we're sampling it twice in that 1 second. So that the sample rate for this would be 2 cycles per second, or 2 hertz sampling rate. If this was 1, this would be 2. And that is the Nyquist rate. That is the minimum sampling rate. Okay. Named after a fellow named Nyquist. And there's a lot of technical reasons for it, and I used to go into it. I'll run this little clip now. This guy pronounces it Nyquist, but and I'm hoping I've shared audio. Let me know if you hear it. As soon as computer wants to hang.
Why is it that though the upper limit of human hearing is about 20 kilohertz, most audio files are sampled at 44.1 kilohertz or more? We tell you why on Digital Ramblings Alive.
Okay, so before I let it go too much further, so he's talking about audio, and we talk about audio a lot when we talk about the fundamentals of sampling in digital, just because it's easier to get your head around. We could talk about sampling and stuff for video, but the frequencies are much higher and it becomes much more abstract. So a lot of the educational stuff when we talk about sampling and quantizing revolves around audio, just so you know.
Hello and welcome to Digital Ramblings Alive. Before we begin, let's have a quick look at how audio files work. Of course, as you know, audio is represented by sound waves. The method used by computers to store and reproduce a sound wave is by sampling an input sound wave at fixed intervals. The number of sample points produced per second is known as the sampling rate. The most common sampling rate is 44.1 kilohertz, which brings us back to our original question. Why this high number if our ears can't pick up anything above 20 kilohertz? This leads us to the concept behind Nyquist rate. This refers to the minimum sampling rate required to reproduce a wave without aliasing. Before we continue, we have a new term here, aliasing. This can be best explained with an example. Here is our original wave in blue. Now let's sample it at a pretty low sampling rate to introduce aliasing on purpose for demonstration. Let us now attempt to reconstruct the wave by joining up our samples with this red line. Do you see the problem? While technically the samples do indeed sample the original sound wave, the reconstructed wave is in no way similar to the first. In fact, the new wave is at a lower frequency than the original. This effect is known as aliasing, and the whole concept behind Nyquist rate is to prevent this from happening. In audio terms, we apply this concept so that audible frequencies do not suffer from aliasing. All that remains to be said is simple. The concept behind Nyquist rate says that you need to sample at double the maximum frequency you do not want aliasing for. Since in the case of audio files, we want all audible frequencies to not be distorted, our sampling rate must be double the maximum audible, that being at least 40 kHz. Right before we end off, here's a related term, Nyquist frequency. While sounding very much the same, it does not refer to the same thing. You see, while Nyquist rate refers to the sampling rate at which a given maximum frequency would not become aliased, Nyquist frequency refers to the maximum frequency that will not become aliased, given a fixed sampling rate. This, of course, means that Nyquist frequency is half the sampling rate. That's all there is for this episode on Nyquist rate. If you have any comments,
Okay, so ignore that last bit about the Nyquist frequency. Again, that's an audio thing we're not going to really get into, but basically what he's talking about is the error won't be noticed at the Nyquist frequency. Let me go back then and just sort of cover it again, just so we're clear. So the reason that we picked 44.1, besides the fact that was the most amount of data that you could put on the CD, is because it's double the 22,000 cycle high-end frequency of human hearing, right? So that's where that number came from. When they said 44.1 K hertz, what they were doing was they took what the maximum frequency humans could sense, which was 22,000 hertz, and doubled it. Why the 0.1, I'm not exactly sure, but it's definitely doubling the highest rate of frequency that we need to hear to get that accurate signal, okay? So that's where these numbers kind of come from. Don't get too hung up on the Nyquist rate, just know that it's a thing. And really it's just to tell you that there is a minimum sampling rate that below which the data gets aliased. And the point of that is that you want to understand that aliasing is not just a video. We talked about video aliasing, I think before, and correct me if I'm wrong, but it's aliasing is any kind of digital to analog comparison where the digital copy isn't the same. And technically speaking, all digital copies have some form of aliasing, because all digital copies are not perfect analog originals. The whole point of all the stuff that we do with compression, with sampling, with quantizing, with increasing data rates is to try to eliminate the aliasing or reduce it to being undetectable. That is almost the entire work. So if you're wondering, for example, why codecs are constantly changing, why sample rates keep going up, then when that video he did was created, he was talking about the standard rate at 44.1. So he's dating himself, because there is no standard anymore. Audio now, if you look at Spotify and others, they'll have 198 kilohertz per second, 132 kilohertz per second. They'll have variable sampling rates that change dynamically with the music. The whole point of that exercise, of all those exercises, is to try to reduce the amount of aliasing detectable to us. In audio, it comes off as odd sounds and strange tones. In video, it's blocking, chunking, all the different things. You see dead pixels, those kinds of things would be considered, well, not dead pixels, but things that look like dead pixels in the picture, bad macro blocks. That's all aliasing, because the data that's being reproduced is not the same as the original. All right. Okay, so hopefully that doesn't confuse you too much. I know this is very abstract today, and it's a lot of talk and not a lot of pictures. I'll try to make it better with this next little chunk. So now we're going to talk about color subsampling. So just to recap again, we've talked about sampling and quantizing, right? Sampling is the rate of sampling is how many times per second, and the quanta is how many bits, how many computer bits are you using to measure that sample. That's really all sampling and quantizing is. And then the last little chunk there to remember is that both the sampling and the quantizing, the stopping to take a measurement, if you will. So think about dipping a cup of water into a sink full of water, is taking a sample, and then the number of measurements on the side of the cup is the quantity. The cup is the same size all the time, but how many stripes are on the side of the cup to see how much water you have? That takes time. And the problem with that is that as you're taking the time to sample and measure, the world keeps moving, right? So we want to sample as quickly as possible. We want the whole process to be as efficient as possible, so we don't miss that much of the real world, because the real world doesn't stop. Okay, anyway, so that's the end of that bit. Okay, so let's talk about color subsampling now. And so what we do, what color subsampling, the reason this slide's up is it's a bit provocative, in that we make color irrelevant by making it redundant. And what that means is that we're going to, all of this is happening before compression, right? So all this quantizing sampling, we haven't compressed yet. And this is why I apologize that this is kind of out of order. This should have come before the compression lecture, but I lost this presentation, I'm going to be honest. And I found it a couple of days ago in the wrong module. Anyway, it's important to understand that before we actually start applying compression schemes, the sample and quanta has happened, right? So now we have if you think about it, the sample and quanta process, the sample and hold measurement process, gives us the numbers to compress. But before we even do that, we decide in advance with video to not deal with all the numbers by doing a couple of things. And one of those things we do is called color subsampling, okay? It's a form of compression in that it reduces the amount of data that we then need to apply to MPEG or other processing, right? It is a kind of a form of compression. But it's a different step. It's a separate stage. So we make the color irrelevant by making it redundant. What does that even mean? We remove the data before compressing. We look at this image of this parrot, right? And we see the feathers. And we go to the feathers a little closer. And you see that every single one of those little macro blocks, right? And I've got this image because it perfectly illustrates the way we look at MPEG. We have all these little macro blocks of pixels, right? And you look at these macro blocks and see there's all kinds of colors, right? But if you go in even closer and look at the individual pixels, I'll show you this. You get this kind of thing happening. All right, so we're looking at 2 rows of pixels. These are individual pixels now. And we look at 4 pixels across those 2 rows. All right, and I'm going to play this again. I just want to show you this first. Okay, so I'm just going to go back and I'm going to stop this and go start it again. So 2 rows of pixels. This is the key to color subsampling. It always starts off with 2 rows of pixels. We look at 2 rows of, and we do this starting at the top of the picture and going all the way to the bottom. So this happens in groups of 4 throughout the entire image, right? This is a continuous event that happens throughout the entire picture, pixel by pixel. So 2 rows of pixels, and then we group them into 4 pixels across. Okay. And I'm just going to stop it when it gets to that. Oh, where's my cursor's gone away? Dang it. Okay. I'm going to stop it here. So what happens now? We remove the picture of the parrot and we just have those individual pixels isolated. And we have 4 pixels across, 4 different colors and shades in each one, right? More or less. Let's say that we have 4 different colors and shades in each one. Okay, then what we do is we separate out the brightness information, because remember, humans are very sensitive to brightness information. So we pull that out. This is the luma down here being removed, right? And then the processing occurs on just the chroma information, just the color data. Okay. And I'm just going to carry on till the end here. So now we have these pixels are just color. And so now what we do is for every 4 pixels in the original, 4 pixels get reproduced. Okay, and that sounds kind of straightforward because this is not compressed. This is kind of the native unadulterated image. In other words, if we did not do the color subsampling, we would have what's called 444, right? So for every 4 pixels in a row, 4 pixels of data in the top row and 4 pixels of data in the bottom row are reproduced, right? And again, that sounds obvious because that's no processing. We're not doing anything yet. We haven't done any subsampling here. But I want to show you this because this graph, this ratio, I'm sorry, at the top of the 3 numbers illustrates you have 4 pixels in a group. That's the first number. The second number in the ratio is the top row of 4 pixels, and the third number is the bottom row. So what you're saying with this ratio is for every 4 pixels, 4 pixels in the top row and 4 pixels in the bottom row are reproduced full color, right? And that is essentially the way the image starts, but not good enough. We need to compress that data a bit more. All right. So I think I'm on the right slide now, but we'll just see here. No, this is the same one again. Hang on. There we go. So then now we need to, so now that 444, if you imagine that we have 4 pixels in 2 rows, first row is all 4 pixels being reproduced, second row is all 4 pixels. Now we want to play tricks. Okay, now we need to do that color subsampling. So now we have the same ratio, same 3 positions, but different numbers. Again, the first number is a 4 because we're going to look at 4 pixels, but you see there's a 2 and a 2 now. So what happens with 4, 2, 2? So we take those same 4 pixels that we had before in 2 rows and we blend, or sorry, we don't blend. We sample only 2 pixels every second pixel in the first row. So you'll notice what happens here. I said blend, that was a mistake. What we do is we take the first pixel, we don't take the second pixel, we take the third pixel, and we don't take the fourth pixel. We don't record that data at all. So we haven't even started compressing yet, right? Hey, Colin, welcome. We haven't started compressing yet. we have the first pixel, we just don't record the second pixel. We have the third pixel and we don't record the fourth. Okay, and that's called 4-2, right? First row. And the result is boom, boom. Now you'll notice that although they're still individual pixels, but for the sake of this illustration, we've blended them together because now that's what actually is recorded. The two pixels are identical. So right away, you can recognize if we talked about redundant data, right? If we're doing compression, we use redundant data, the second pixel is right away the same as the first. So now we can save space. We don't need to record that data. We'll just reproduce the first pixel again. And then we change it when the third pixel shows up. So we've already cut the amount of data in half on that row. And then we do it again to the second row. Okay. So we'll process the second row. Again, we take out the chroma information, the brightness, right? We're just talking about the color here. And now we go to the second row and do the same thing, right? So now we take the first pixel in the second row. Don't jump yet. We take the first pixel in the second row and we don't record the second pixel. We record the third pixel, but not the fourth pixel. And this is called 4-2-2. And 4-2-2 is by and large, the most common digital color subsampling scheme. So let me stop for a second and explain. 4-4-4, as I explained before, is all the pixels that were captured. Every pixel, so for every 4 pixels, that's the first number in the ratio, 4 pixels are reproduced in the top row and then 4 pixels in the bottom row. So 4, 4, 4. Now we're going to compress that. So pre-compress, if you will. Color subsampling is a more accurate term. And we're going to say we're going to sample the colors for every 4 pixels in the first row twice. Okay, so you have the amount of data in that first row already. And then we'll do it again. Now, when I say have the data, I'm talking the color data. The luminance data is still the same, right? So that luminance that was split out, and I'm going to go back to where that is in the illustration. Oh, this information, oh, there it is. Oh, hang on, stop. This information here is separate data. This data is the brightness for each pixel, and that is not affected by color subsampling. We're only talking color samples. This brightness data is still recorded completely, and because, remember, humans are much more sensitive to brightness changes. If we were to play with the brightness data, and some older compression schemes used to, and some of the newer ones do kind of as well, we would notice it much more obviously. So we're very careful to preserve the brightness data from the sensor, from that shot of the parrot that we go back to the beginning, and don't mess with it. We just store it away. Okay, so when we talk about 4-2-2 at half the data, it's half the color data, but not half the overall data, right? It's only half of the color data. All right, clear? So then there's one more step you can take, and this is kind of a cheat, and you'll find this with some cameras, some phones, etc. Use something called 4-2-0. And what 4-2-0 is even more compression, in that now what we do is we take, pause. We take that first run and go back here and show the illustration. For every 4 pixels in 4-2-0, in 2 rows, remember, we're always talking 2 rows. In every 4 pixels, the top row, we sample 2 pixels, just like the last 4-2-2 scheme. But in the bottom row, we sample none. We don't sample color in the bottom row at all. Okay, and so we end up with this kind of effect, where now we've got, oh, hang on. Now we've got a block of, come on, too much lag in my machine here. I'm trying to pause it there. Oh, pause. All right. Now we end up with this. So 4-2-0 gives us these. Now remember, these 2 squares you're seeing are 4 pixels each square. 2 pixels on the top row, 2 pixels in the bottom row. But the color data is only 2 bits of color data in this whole array of pixels. So before we even start applying MPEG or JPEG or whatever compression to it, we've already done a color subsample. And this data, this 4-2-2, this 4-2-0 data is gone forever. It cannot be recovered. You cannot go back to 4-4-4 once you've advanced to 4-2-2. So if you're recording in a camera that's recording in 4-2-2, you can never go back to 4-4-4 because you never recorded that data. This is before the compression happens. So before MPEG compression even sees this pixel to deal with it, the data's gone, bye-bye. Have a party for it, send it a card, farewell card, because it's gone forever, okay? 420, it was very common in DV. It's very common in some action cameras, some phones, because again, it's close, quote unquote, good enough. There's enough color data, you know, to make an image that you can send to grandma on your phone. But as a professional, I would never want to shoot in 420. And be careful, because some cameras, even to this day, as you turn down the compression, in other words, as you go to higher compression schemes in the camera, sometimes this starts to happen, and you have to check your camera's specs that you're not switching to 420. Okay. It's not a function of the camera chip. This is the circuitry after the chip and before the compression, just so you know where it sits. All right. So I'm going to just move on here for a second. Oh, all right, stop. And then just to confuse you some more, there's some more numbers. Now you'll see there's actually 3 sets of numbers, or 4 sets of numbers. And this is for alpha. I don't have to go full screen, but 4444 indicates that you're dealing with an alpha channel. So you wouldn't see this in a camera, because cameras don't record alpha. Anyone who's not familiar with alpha, it's that whole cutout channel that you use in Photoshop. It's also called the matte channel. It has a bunch of other names. But if you're doing computer animation, if you're doing digital animation, you need that 4th 4, because you need to preserve the data in the alpha channel. All right. Again, you won't deal with this if you're shooting. It's only kind of a thing if you're doing graphics or animation, that kind of stuff. But it is important to remember that there are going to be times when you need to preserve that 4th channel, that 4th, I guess it's a channel, it's a 4th layer. It's hard to explain. So the first 3 numbers are still 4 pixels, top row, bottom row, but that 4th number represents the alpha channel. And this is just an FYI, as I say, but understand that it does exist. All right. Okay, so I'm going to stop share, pause. I hope that helps. We'll go back and share some more and carry on. It's going to be a thick morning this morning. Okay, so right away, we're going to talk about errors. And here I've got I don't think this actually moves, does it? Even though it's a video clip. Now I've put all these clips in a section, in a module this morning for this presentation. So what this is showing here is if you have critical patterns, so this is really hard to visualize, but if you have patterns that have alternating pixels, right, where that pattern is important, color subsampling can alter the pattern, right? If the color subsampling is not done properly, you can get sort of odd errors. Again, this is a bit abstract, and I wish I had a better illustration. Let's look at this. Here's a real world example of a subsampling error, right? So if we look at this green screen, right? Now we've keyed out the green, but look, we've done some color subsampling. We're doing 422, right? Oh, and by the way, you recognize this is 422 because we started with 4 pixels, right? And you'll notice that even though, because it's a green screen, so here's the thing, because it's a green screen, not every color is going to be individually different at the back because the green's all the same green, right? But we're still looking at all 4 pixels in the original. This is 444 here. Now, if we play it and go to 422 subsampling in the camera, and now zoom in, and it's hard. Let me try to go full frame. Can I go full frame on this? No, it won't let me. I don't think. No, it doesn't work. But I'll stop it here. If you can and do this when you have the video in front. Oh, come on. I'm just not fast enough today. Oh, there we go. Okay. It's really subtle here, but if you zoom in, you can see the green fringing. Do you see the green fringing around the hair of the Wookiee doll? Right? Well, that's color subsampling, because what it's done is it hasn't sampled every pixel. It's sampled only every second pixel. This is 422 we're using. And because every second pixel has a bit of green in it, because of the green screen, we're not capturing all those pixels accurately, which means the keyer in your Photoshop software or your TriCaster, whatever device you're using to create this key, doesn't have all the color information it needs to do a clean transition between the brown hair and the green screen. Right? So you get this green fringing. So this is where I went back to the 444 and the 4444 that graphics one, that fourth 4 means that you're getting a full sample of the key whole. In other words, the chroma key whole that is created by the chroma key is accurate. Now you have, if this video had been sampled in 444, we wouldn't have this green fringing. So this fringing that's on here now cannot be removed, right? There's only 2 ways you can do this. One is you can expand the chroma key to cover some of that hair, which means you're going to lose some detail on the doll, and the key might look kind of weird. Or you can hand color all that green to brown and make a cleaner edge. That's the only way you're going to fix this. So color subsampling for things like alpha keys, chroma keys, blue screen, green screen work is really crucial if you want a clean, crisp key. Now, if it doesn't matter, remember, in the wide shot, if we go back to the wide shot, I don't know if we can see it here before we get, no, I don't think we do. But okay, here we go. Stop. Okay, so here's the wide shot. If you really squint, you can probably see a little bit of green at the top of the head, but it's still, now we're still the same color subsampling, right? But at the wide shot, you don't notice it. So again, do you care if it's 444 here? Maybe not. But if you're going to do a zoom in, if you're going to do a tight shot of the person, if you're going to have somebody in the foreground go by and fill the whole frame with their body as they cross in front, and you're going to be able to see that edge much more clearly, and the 422 then you might start seeing this fringing that's back here, right? So there you go. It's not a good thing or a bad thing. You just have to understand the trade-off. Now, data savings, just as an example. So remember, 444 is all the data, right? That means we're not subsampling anything. We're fully sampling. So subsampling just means we're sampling less than normal, right? Subsampling, below sampling. So 444 isn't subsampling at all. It's full, all pixels are measured. And not only measured, stored. They're all measured anyway. So I should be clear. All that sample and quantization happens before this. This is where you actually discard the data. You have to, because you have to have the data to discard, right? You can't do this before you measure. So you measure, and then you do 100% translation 444. Now, if you took every second pixel and merged them in color information, you save about 66%. So remember what I said, that 422 is every second pixel. So logically, you're thinking, well, that's half the data. No, because remember, in that data is the luminance information, which is preserved. That's that 13% or so of this, or pardon me, 16.7%, like I need to approximate, of the data that is remaining is the black and white information, the Luma data, right? So we have half the color data and we have the Luma data on top. And then 420 is truly, oh, come on, big reveal, big finish, everyone. There. So 420 really is half the data because there's so little color data compared to the luminance data. So remember, the luminance data in all 3 of these graphs is preserved. And if we assume, we don't know for a fact, but if we assume the luminance data based on that middle column is at least 13 or 15% of the information, if we subtract that 13 or 15% from the 50, right, we're down around 30-something% of the data color data is preserved to be recorded. And then remember, so after this, MPEG happens and mangles it up even more. So the whole idea that the color subsampling can be dangerous if there's a lot of compression that's going to go on as well, because you're going to have a lot of math going on, and that math will have errors because it won't have the original data to play with. All right. So that's color subsampling in a nutshell. And then here's some quick illustrations just to show you, if we look at lines of video, these are the same things again. And again, sorry, these are a bit out of order. So 422, the top line is Y, which is luminance. If you remember that Y is the symbol for Luma, every single pixel in that row is sampled, right? But in 422, only every second pixel in the row is sampled, okay? And then 444, every row, every pixel, right? So there's no subsampling going on with 444. That is full color, okay? This is your ideal. 444 is your ideal, and we move towards this. We started with 420, we went to 422. We're now, we're hoping that we can eventually start recording things at 444, but practically speaking, we're still not there. And then 420, the bottom one, you'll see that the first row of pixels, all the black squares are there still because the luma is all recorded. And then every second pixel, right, 4:2. And then the bottom row, no color data is recorded at all, but there is still that black dot, which is the luminance data. So we still have the black and white data. Excuse me. We still have the black and white data for the second row. And then there is a scheme called 411. It's usually a thing for things like security cameras. It's really crappy. And this is where you only record one color pixel in both rows. It's even less data than 420, but we'd never use that in any kind of sort of broadcast environment. All right. Whew, we made it through that. So now let's talk about color depth a little more. So talk about sample rate, just to recap, measured in hertz. 44.1 kilohertz is the music sample rate, as I've said before, 44,100 times a second. The quanta is how much data, right, is reserved to measure with. So remembering that we're not talking about changing the total amount, we're just talking about how many steps. And that is called the bit depth. So in color, the bit depth, we automatically, with the 8 bits color, we have 8 bits of depth, right? And we know that we have 8 bits of depth for each color. So technically, if you think about it, there's actually 24 bits there. And sometimes this is referred to as 24-bit color because you have 3 colors, 8 bits each, that's 24, right? But for now, we're going to talk about 8 bits per color. So we have 8 variations, 8 steps in each color. And you can see that the bottom on the right-hand side, you see the examination here, the example here, we have 8 bits of color. And you notice the steps between the colors? See, this is what happens when your quanta isn't as accurate. This is color aliasing right here. The transitions between the colors are quite abrupt in 8-bit color, right? And they are. Now, when you blend them all together for 24 bits, these transitions do get much smaller. So 8-bit color is good enough. We've all watched 8-bit color. We watch it every day, all the time when we watch video, and we don't see these steps. But these steps, if you exaggerate them a bit, are here. And in 10-bit color, the steps get much narrower, so that the steps between colors, the colors don't go anywhere, really. They're still in the same places, but the steps between them get smoother, right? Because you have more data. You've got 2 more bits per channel to express your colors. So, and I said it's called 24 bits, so we'll skip that. So remembering that 8-bit color, we're just going to quickly recap this. 255 is the largest decimal number. That means there's 256 colors because all zeros is also a value, which is black, right? So 256 values for each primary, right? Which means that we do some math, that we have 16 million colors in 24-bit color space. Okay. 8 bits red, 8 bits green, 8 bits blue is 24 bits, right? And if you do the math and multiply the values, you get 16 million colors. And then again, just to recap, this is an illustration of the color space. The yellow triangle is 8-bit color, 24-bit color space. So remember, 8-bit color, 24-bit always assumes RGB. It's not 24 bits per color. It's 8 bits times 3, okay? So they can be used interchangeably. More often than not, we call it 8-bit color because we're talking about individual colors, and colorists in particular want to talk about individual colors, not colors as a whole. But people who market things, to sell things, like bigger numbers. So they often use 24 bits because it makes their monitor, their camera, their equipment sound better. Oh, it's got 24 bits, not that 8-bit stuff. Well, it is 8-bit stuff, right? And if anybody tells you, by the way, that 24 bits is better than 8-bit color, then walk away because they don't know what they're talking about. There's no such thing as 8-bit. I mean, not since the days of Mario Kart is there 8 bits only, right? Which there isn't. There's 24 bits is 8 bits per color. So 8-bit color. And then a quick illustration of the HD. Yeah, we've talked about this before. This is just a quick recap of the 2 color spaces showing 8-bit and 10-bit, just as an example. And 4K is pushing forward with 10-bit. So we have the bigger black triangle with the bigger color space. More colors are captured because we have more data, right? So remember, if this runs counter to what you might have already thought, remember that CIE diagram never moves in size or shape. that bigger overall curved triangle never moves or changes. What changes is the amount of colors inside that triangle we can deal with. And 10 bits just means more. So it's not only more steps per color, but more data to describe colors, right? And that means that your triangle gets larger. It's instead of having 256 values, you now have 1,024 values, right? Because you're doubling it twice. You double it from 8-bit to 9-bit, which 9-bit takes you to 512 values, and 10-bit takes you to 1024. And then 1024 bits means blah, 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 plus, 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 math, 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 that you have 1.7 billion colors total. Okay, so more than double the 16-bit, more than 16-bit plus 16-bit, right? Plus 16-bit. So more than even triple 16-bit. What did I say? Why do I keep saying 16-bit? Let me try that again. Take two. More than double 8-bit color. 16 million colors. Oh my God, I need more coffee. 16 million colors. It's more than double or even triple that, right? If you tripled 16 million colors, you wouldn't get a billion. Okay. Done. Stop. Stop recording.